In this video, we will define differentiable manifolds and see some examples of them. First, we will review some facts about topological spaces, then define differentiable manifolds, discuss what charts, transition functions, and atlases are, and then give simple examples mostly from surfaces that are embedded in three-dimensional space. So as an overview, let's see what differentiable manifolds are. In the beginning, we start with topological spaces, and we require that they are locally like Rn. That means that all their points can have coordinates in Rn, and these are called local coordinate systems. There are many such coordinate systems, and when we transform coordinates from one coordinate system to the other, we require that these maps are differentiable. This gives a differential structure on the manifolds, and using it, we can define things like the rate of change of functions on curves. From them, define vectors, and from them, define one-forms and tensors as linear maps on the vector space defined by the vectors. Defining tensors at all points of the manifolds or the manifold defines tensor fields, and as special cases, vector fields and one-form fields. From vector fields, we can define a derivative, the Lie derivative, and from special cases of tensors called differential forms, we can define integration and another derivative, which is called the exterior derivative. So the differentiable structure allows us to do things like differentiating and integrating. But if we want to do classical general relativity, we need to add additional structure to those manifolds. The first layer of additional structure is the affine connection. The affine connection basically defines parallel transport of vectors along curves. And from it, we can define covariant derivatives, geodesics, and finally curvature. And curvature, as we know, is the observable field in classical gravity. But in the classical theory of general relativity, we need to define what geometry is. We need to define how to measure distances, and for that we need additional structure, which is called a metric. A metric has associated with it also an affine connection. So given that metric, we can have all the nice things that we described that an affine connection gives us, like parallel transporting, covariant derivatives, and curvature. The metric gives us the dynamics of gravity. We have to understand this. When we will do classical general theory of relativity, we choose a manifold with its differentiable structure as a background. This does not change. But then we consider this additional structure endowed by the metric. Since there are many metric tensor fields that we can define on a manifold, we have to choose the one that is given by the dynamics of gravity. This is obtained by solving the Einstein equations that will give us a metric that exists in space-time, and we will use that metric to do all those things will allow us to do physics, like differentiating, integrating, and other things that we will see later. Some very simple example of manifolds can be briefly mentioned here. First, by definition of the manifold, all the Rn spaces are manifolds because they are globally equivalent to themselves. So R1, which is the straight line, R2, which is the plane, R3, which is the space, etc., are all differentiable manifolds. but they're less trivial examples like the ones of the n-dimensional spheres. The one-dimensional sphere is the familiar circle, whereas the two-dimensional sphere is what we usually call sphere in everyday life. Other manifolds that are of interest are the toruses, like the two-dimensional torus, which when looked in a three-dimensional space, it looks like a donut. And but the concept of manifold is much more general than those spaces. And for example, Lie groups, which play a very important role in physics, are cases of differentiable manifolds. For example, rotations or Lorentz transformations are differentiable manifolds. Manifolds can be constructed by taking the product of two different manifolds, M1 and M2. So if M1 and M2 are already differentiable manifolds, by taking pair of points from each one of them, we can form a larger manifold, which is the product of those two. A very simple example is the cylinder. The cylinder is the manifold that is equivalent to the product of the circle with the straight line. You can see that by taking the straight line here and considering a circle depicted here as defining a plane which is vertical to the straight line. And as you move it along the straight line, you swipe the whole cylinder. So the cylinder is equivalent to this product. Other examples is R2, which is R cross R, Rn, which is R cross R and times, and the two-dimensional torus, which is the product of two circles. Here are examples of spaces that are not manifold. It is worth mentioning this example here because it is not a manifold at a much lower level than the differential structure or the local equivalence to Rn. So this is a so-called non-Hausdorff space, and that is why it is not a manifold. So what we do here is we take the line, we split it in two lines, but we identify those points here. So we have the usual topology of the lines here, but a point here and a point there have no separate neighborhoods. That means that we cannot find open sets that are mutually exclusive that contain the points P1 and P2. And this is something that we would like to have as a fundamental property of the differential manifold. That means every point, P1 and P2, have neighborhoods that are distinct from each other. Now the second line shows as examples manifolds that are not locally equivalent to some Rn everywhere. Of course, the line here is equivalent to R1, the plane here is equivalent to R2, but it's not possible for their union to define a manifold that is everywhere equivalent to some Rn. Similarly, for those two cones that are, their tips here are on top of each other. A special category of spaces that are not manifolds, but are very close to being manifolds, are manifolds with boundary. So the simplest example is to take a line segment on the real numbers, but also include the endpoints of the interval, this one and that one. So this is not a manifold, but it is a useful space, and it is a manifold, and we call it a manifold with a boundary. Similarly, if we consider a disk on the plane, and we include both the interior and the boundary, which is a circle here, then we obtain a disk with a boundary, which is also not a manifold, but it is a manifold with boundary. Another example here that may be counterintuitive is the single cone. although the two cones here do not form a manifold, this cone here actually is a manifold, and it is a manifold which is equivalent to the plane. The fact that we see something singular here on the tip is not coming from the differential structure of R2, but it comes from the choice that we made of how we measure distance on the plane. So this choice has a singularity here on the tip. It gives, as we will see later, infinite curvature. But otherwise, this manifold is very well defined. Let's remember some very basic facts about maps that will be useful. So what is a map? If we have two sets, M and N, then a map phi associates to every point on M a point on N. So M is called the domain of the map, and N is called the codomain. The set of points on N, which the points on M are mapped onto, is called phi of M, and it's called the range or the image of M. Special cases for maps are maps that are onto or surjective. So if the image of M is the same as the codomain N, then we call the map onto N. A map is one-to-one if 2 points here have different images on N. Of course, for a map, it's not allowed for a point on M to have 2 images on N, but 2 points on M can have the same image on N. So if these are distinct for all points on M, then the map is one-to-one. And if the map is both one-to-one and onto, then it's called bijective, and it is invertible. That means if we take the inverse map from N to M, this is also a map. Now let's recall some basic facts and definitions from topology. If anything that I say from now on sounds unfamiliar to you or difficult to understand, then you have to open an elementary book on topology and review those concepts and understand them. So let's start by saying what is a topological space. So M is a topological space if it is endowed with a structure that comes from unions of sets, which we call open. And this union of sets, this set of sets, has to have the property that if we take the intersection of two of such members, or in fact the intersection of any finite number of those, then this will also be an open set. That means a member of this set of sets. And if we consider the union of those sets, the intersection here, and the union here, of any number of sets, even infinite of those, then this will also be an open set. An example that will give us the usual topology on Rn is the open ball. The open ball in Rn consists of all the points that are at distance less than r, strictly less than r, from a given point x0. So the usual topology on Rn can be obtained by considering all possible balls in Rn, and the open sets are the union of any of those. A topological space is a Hausdorff topological space if any of its points have open sets U1 and U2 that contain those two points, but their intersection is the empty set. We call any set, open or not, a neighborhood of point P if there is an open set contained in W that contains the point P. A set in M is closed if its complement with respect to M is an open set. We call W bar the closure of W if it is the smallest closed superset of W, and the interior of W if it is the largest open subset of W. The boundary of W is the difference between its closure and its interior. A set W is compact if it has an open covering. That means a set of open sets that their union is larger than the set W. If every such open covering has a sub-covering that has a finite number of sets inside it. To understand what compact sets are, there is a theorem in Rn that states that if a set W, subset of Rn, is compact, then W is both closed and bounded, and vice versa. So, for example, the closure of the open ball that we considered before, which consists of points that are at distance less or equal than r from a point x0, is compact. Similarly, the n-dimensional sphere is also compact because it can be embedded in a one dimension larger than Rn, and in that set it will be both closed and bounded. Another operation in topology that is of interest is called compactification. Loosely speaking, if we start with a non-compact space and we can add a point or do some other operation of cutting and pasting of spaces, and we end up with a compact space, this is a compactification. In this example here, we consider the sphere with its cap missing, its northern cap missing. So as we shrink this cap to zero size in a continuous way, we obtain equivalent spaces. Then we end up with a space that is a sphere with just one point missing. So this and this space are topologically equivalent, and they're both non-compact. But if we take this point here and we add it to the space, then we obtain a sphere, and the sphere is compact. So by taking R2, the plane, or here a sphere with the cap missing, and adding one point, let's call it infinity, then we obtain S2. A subset of a topological space is called connected if there are no open sets such that their union gives W. Sorry, there are no sets U1 and U2 that their union gives W, and their intersection is the empty set. And it's disconnected if it is not connected. A set W is simply connected if all loops that can be drawn on this set are contractible in a continuous way to a point. So, for example, the plane or the two-dimensional sphere are examples of simply connected spaces, because if you draw any loop, you can make it in a continuous way vanish to a point. But if you take the plane and remove a point, or if you consider, for example, the circle, these are non-simply connected spaces, because there exist curves that here they wrap around this point, or here they wrap around the circle, that are not contractible to a point. The notion of continuity is central and arises from the topological structure of the topological space. So if you have two spaces, topological spaces, M and N, and a map phi that maps M into N, then the map phi is continuous if and only if every open subset of N has an inverse image with respect to phi in M which is open. So this can be dizzying if hear it for the first time. So, well, you have to spend the night meditating on this. But let's see a simple example of why this works to differentiate non-continuous maps on the real line from continuous maps. So let's take this very simple map, which is not continuous at x equal to 0. It consists of those two half lines, but the point here is the domain of the map and has image 1. This point here does not have an image map. So here you can see that if you take an open set on n, this is the set n, the real axis, vertical real axis, and you take the interval from 1/2 to 3/2, that is an open set, then the inverse image with respect to f is giving you the half-closed interval 0 to 1/2, and this is not an open set of M. Notice also that the reverse is not true, and continuous maps do not necessarily map open sets to open sets. And the trivial example is given by the function x squared, and you see that if you take the interval here around 0, then this is mapped to the half-closed, half-open interval that contains 0, extends up to e squared. And this is not an open set, but the map is continuous. An important and special case refers to maps that are continuous everywhere on the set M, but they are also invertible, with the inverse map also being continuous. Then this map has a special name because of its importance, and it is called the homeomorphism. And the two spaces M and N are homeomorphic. That comes from the Greek word homeos, which means they are the same. And they are the same in the topological sense because the topology of N is actually the same as the topology of M. So we see here examples of homeomorphic spaces, the one that we discussed before, the sphere with the northern cap missing and the sphere with one point missing. And of course here you can add the plane, the whole plane R2 as being equivalent to the sphere with the cap missing. So this is not equivalent to the sphere, because if you add here a point, you obtain a topological space which is not homeomorphic to the plane. So homeomorphisms allow you to deform spaces in any way you like, but you're not allowed to include punctures, cuts, gluing, and such curves, such operations that are not make those spaces homeomorphic. So let's move on to see what differentiable manifolds are. So differentiable manifolds are actually topological spaces, and they're Hausdorff, that locally are like Rn, but they have additional structure that gives us a differential structure, which is important for what we want to do in physics. So we have already said what we mean by the fact that M is a topological space and a Hausdorff topological space. Now let's explain what it means to be locally like Rn. So locally like Rn refers to homeomorphisms between open sets of M and Rn. This will not be possible. This may not be possible to be done over the whole manifold, because then it would have been equivalent to Rn. So we require that this happens only on open sets that are locally like Rn. So every point P of M is at least in a chart defined by a pair of an open set that contains P, a neighborhood of P, and an invertible map chi, which is a homeomorphism that maps this neighborhood U into its image in Rn, which we call chi U. And this is required to be a homeomorphism. So the point P is mapped to n tuples of real numbers, which we call the coordinates of the point P. The fact that chi is homeomorphism, it means that it is one-to-one, onto, continuous, and so it's inverse map that takes a set of coordinates, set of n numbers, to a point P on the manifold M. So the request that chi is a homeomorphism makes the neighborhood of the point U and its image to be topologically equivalent to Rn. The differential structure is added by considering coordinate transformations. So the charts are not unique, and the point P may belong to different charts. That means we have a chart defined by U alpha, chi alpha, and U beta, chi beta. That maps this neighborhood of P, we call U alpha, to its image, chi alpha of U alpha, and U beta, here to its image, chi beta of U beta. So since P belongs to both of them, then the intersection here is an open set. That comes from the definition of by requiring that M is a topological space. So if we restrict those maps, chi alpha and chi beta, onto this intersection here, then we obtain an image that is restricted to those sets shown here. So then we have a map that relates the coordinates of the point P in this coordinate system to the coordinates of the same point P to that coordinate system. So let's call for the moment those coordinates x mu in the chart chi alpha and x mu prime in the chart chi beta. The fact that the maps chi alpha and chi beta are invertible allows us to define a map going from x mu to x mu prime. For that, we can use the inverse of chi alpha and go from x mu to the point P, and then use chi beta to go to the coordinates x mu prime. So this map is denoted by this, what is written here, and defines a function from a subset of Rn onto another subset of Rm. So if this map is differentiable, then we have the first step of defining a differentiable manifold. Of course, what differentiability means is a matter of definition, and usually mathematics books define a map to be CP differentiable if all those derivatives exist up to order P and they are continuous. This map, if this map is analytic, we use this symbol here, C infinity. And well, we physicists don't worry about that so much. We usually say that we have a C infinity map, and if not, we assume that all the derivatives that we write in our formulas exist and are continuous. So if we have a set of charts where the sets U alpha cover the whole manifold M, then we call this an atlas of M, with the understanding that all these charts are compatible, in the sense that all coordinate transformations exist and are differentiable. If we consider all possible coverings of M such charts, you obtain a maximal atlas. And M, topological space, with a maximal atlas is a differentiable manifold dimension n, where n is defined by the dimensionality of the sets that neighborhoods of M are mapped onto Rn. So let's make some remarks that are useful for us pedestrians in mathematics. So we're usually thinking of manifolds as embeddings, actually Rn. For example, two-dimensional surfaces, three-dimensional space. But the definition that we have given does not makes the manifolds to exist independently of any embeddings. So although embeddings can be a useful tool to define or visualize manifolds, they are not a necessary structure that we need to consider. So for example, space-time will be a four-dimensional differentiable manifold, but this manifold, although embeddable into R8, does not need to be embedded anywhere for us to exist in space-time. So even though we define some space-times by their embeddings, the embedding space has no physical meaning. There is no way to, quote, communicate with it. Furthermore, manifolds can be embedded in different ways, and the manifold is not tied to any of those. So for example, we can embed the two-dimensional sphere to R3 as a sphere, or as an ellipsoid, or as a potato. And all those different embeddings define the same manifold M. Another point that is important is that manifolds may need more than one chart to be covered. It's only Rn that trivially needs only one chart to be covered, but other manifolds like the circle, the sphere, torus need more than one chart to be covered. And we will see that by looking at some examples. So the first example, kind of trivial, but it will help us understand some of the concepts that we introduced before, is the example of the circle. So the circle can be defined by considering the sets of points on the plane given by Cartesian coordinates x and y, such that x squared plus y squared is equal to 1. So we can define a coordinate system for such points by considering the angle theta that the position vector of the point P forms with the real axis, and then map this point xy to this angle theta. So this is a chart which is differentiable, but it doesn't cover the whole circle. And you can see that the eastern point here has to be excluded, because as we move around and make a full circle, we arrive from the other side with theta having values equal to 2 pi, and this is not continuous. So the point E has to be excluded from this chart. Otherwise, the chart is behaving very well. But we can consider another chart that covers now the circle except the western point, W. Then we can map a point on the circle to an angle theta, but now theta being restricted between minus pi and pi. So this map is also differentiable, and very well defined on the whole set U2. The coordinate transformation or the transition map can be easily defined. Of course, it has to be defined on the intersection of the domains of those two functions and has to exclude both the points E and W. So if we consider the transformation from the U1 chart to the U2 chart, then we have to use the inverse map, chi1, go to the point P, then use chi2 to obtain different angle. And you see that those two angles are related by this very simple relation. And you see that this map is differentiable. We also notice that if you take both those two charts, the sets U1 and U2 cover the full circle. So this is an atlas of S1, and we see why S1 is a differentiable manifold. But it's not the maximal atlas. There are many more atlases that we can define, and another one that is of interest can be defined by projecting the points P of the circle onto the x-axis the way shown here in the figure. Consider the north pole of the circle and the line connecting N, the point P, passing through N and the point P, and this line intersects the x-axis at the point U. So we consider U to be a coordinate of P in this coordinate system. And if you do some elementary geometry, you see that the coordinate U is connected to the x and y coordinates of the point P through this relation. You also see that U ranges from minus infinity to plus infinity. Now, as long as the particle, as the point P moves on this quadrant of the circle, see we start from this point, U equal to 1, and as we move around, this point U moves away to infinity as P is approaching N. So you see this coordinate system is not well defined when Y approaches 1. There's no problem with any other point of the circle though. So this chart covers the whole circle except the North Pole N. We also see from simple geometry that x is equal to cosine theta and y is equal to sine theta, and we find that u is related to theta via this relation here. And also note that we just proved that the circle without the North Pole is topologically equivalent to the real numbers. Or for that matter, since we cut open the circle here, you obtain an open interval, any line segment, without its endpoints of course, equivalent to the whole real numbers. So we have found a map from the point xy to the coordinate u, and we also have a coordinate transformation between one of the theta coordinate systems that we defined before and the u coordinate system given by this relation. See that this transition map is differentiable. So this is an admissible and compatible chart, the ones that we defined before. But we can do a similar projection using not the north, but the south pole of the circle. So we consider the set, which is the circle S1 with the point S removed. And then we consider the line that passes through S and P and cuts the real numbers here at the point V. So we define V to be the coordinate of the point P. And again, if you do simple geometry, you can find these relations of the relation between x and y and v, which is given now by this one, which differ from that one just by the sign here, denominator. Of course, you see now that the map is not well defined as y gets close to -1. So if the point P approaches the south pole, then we have this point moving to infinity. So indeed, this chart is not possible to cover the whole circle. Also, using the relation between theta and x and y, we can find the relation that connects theta to this new coordinate v. So we have the chart, the coordinate system defined by chi4, giving us the coordinate v, and we have a coordinate transformation from theta to v. So the transition function here can be easily seen to be differentiable. But it is easy to see that the transition function between the u and v coordinate system is also differentiable. You don't actually have to invert those relations to do that. It's very simple algebra. Just multiply u and v and find that because the point P is on the circle, this is equal to 1. Therefore, v is 1 over u. So the transition map that takes us from u to v is simply 1 over u, and it is differentiable in the domain of that function. It is also easy to see that the union of u3 and u4 is the whole circle S1. Therefore, the two coordinate systems define an atlas on S1. So you see that so far we have not been able to find an atlas that contains less than 2 charts. And in fact, it is not possible to do so because S1 is topologically inequivalent to the real numbers. So let's move one more dimension up and consider the two-dimensional sphere. So let's define the sphere as the set of points in R3 whose Cartesian coordinates satisfy the relation x squared plus y squared plus z squared is equal to 1. So we can define an atlas on the sphere by considering hemispheres of the sphere in different directions and project those hemispheres onto the disk, which is vertical to the direction that we have chosen. So let's pick up as a direction of defining the hemispheres the z-axis, and we have 2 charts, the UZ plus that contains all the points of the sphere in the northern hemisphere, which are the ones that have their z component to be positive, and we project those points to the xy plane and define as their coordinates in this chart to be x and y. So the point that has Cartesian coordinates in R3, x, y, and plus square root of 1 minus x squared minus y squared is mapped to the pair of coordinates x and y. We can define a similar coordinate system in for the southern hemisphere by considering the points whose z coordinate is negative. Notice that this is strictly positive and strictly negative, so we don't include the equator. By projecting those points onto the same xy plane, then those points here have coordinates in this chart to be x and y. So you see these are 2 different charts giving 2 points in the north-south poles of in the northern hemisphere and southern hemisphere of the sphere to have the same coordinates, but they actually belong to different points on the sphere. So we can do the same construction by choosing the y-axis as being the direction that defines the hemispheres. So The two hemispheres now are defined by points that have their y coordinate positive and negative respectively. And all those points are projected onto the xz plane such that a point like this one has coordinates in this coordinate system to be x and z, and the same thing for the left hemisphere defined here. Last but not least, we consider as the direction that defines the hemispheres to be the x-axis. These are the set of points with coordinates x being positive and negative respectively, and all those points are projected onto the yz plane, giving y and z coordinates to each one of the two hemispheres. You can easily work out coordinate transformations between the two, any pair of those charts, and it is a nice mental exercise to do so. So let's consider a coordinate transformation from the x plus hemisphere to the y minus hemisphere. So this will start from this coordinate system, giving us coordinates for the same point into the y minus, which is this coordinate system. So you see that a point with coordinates y and z in the x plus coordinate system will be mapped to coordinates x and z in the y minus coordinate system, such that x is equal to the plus the square root 1 minus y squared minus z squared, and z is mapped to itself. And you can easily see that this map is differentiable. Observe also that we need all those 6 charts to cover the whole sphere. So in order to make an atlas, we have to consider all those 6 charts. So one may wonder if we need that many charts to cover the sphere S2 for all possible choices. And the answer, as we will soon see, is no. We only need 2 charts. But as a step forward to that direction, let's consider a very familiar coordinate system for the sphere, coming from the spherical coordinates of point x, y, z. So we consider a coordinate system defined on this set. I call it U theta, which is the sphere minus this half circle here. So that maps the xyz point to theta and phi, where theta ranges from 0 to pi and phi ranges from 0 to pi, without the endpoints being included in the domain. And the relation between x, y, z and theta and phi is given by this very well-known relation. So every point is mapped to a one and only one pair, theta and phi, and vice versa. So this is an admissible chart of the sphere, which is compatible with the charts that we considered before, defined by hemispheres. So, for example, if you consider the coordinate transformation from theta phi to x and z in the y plus hemisphere, then theta and phi is mapped to x and z, with x given by this relation and z given by that relation. But theta and phi are restricted now, don't cover the whole sphere, but they cover the respective hemisphere. So theta is ranging from 0 to pi, but phi is ranging now only between 0 and pi, 0 and 2 pi. The inverse transformation can also be computed. Be found to be those nice differentiable functions. But now let's see how we can define other charts that cover a larger proportion of the sphere. So like in the case of the circle, it is possible to define charts on the whole sphere, but without a point. So let's make a projection of the sphere onto the plane using a similar procedure that we followed in the case of the circle. So let's consider the line that goes through the north pole of the sphere here and the point P under consideration and its intersection with the xy plane marked by the point UV, where U and V are the x and y coordinates of that point. So U and V are defined to be the coordinates of the point xyz in this coordinate system. And by doing a similar exercise, like in the case of the circle, you can find the relation between x, y, z and the coordinates u and v. And they're equal to this. We can see that this chart is compatible with the ones that we have presented before by considering the coordinate transformation from the theta phi coordinate system to the UV coordinate system. And this is given by those relations here, which are nice and differentiable. Similarly, we can project the sphere onto the plane by considering a projection that uses the south pole instead of the north pole. So here we consider the line that goes through the south pole and the point under consideration, and the point ST on the xy plane, which is the intersection of this line with the plane, defines coordinates S and T for the point P. You can show that the relation between x, y, and z and S and T is this one, which is defined everywhere except at the point where z equal to -1, which is the south pole. And this chart is compatible with the rest because this relation here that gives the coordinate transformation from the theta phi coordinate system to the ST coordinate system is well defined and differentiable. You see that those two charts form an atlas on the sphere, because the union of UN and US covers the whole sphere. It is also minimal because we cannot find any atlas that contains less than two charts. We can also compute the coordinate transformation from the UV coordinates to the ST coordinates by doing this simple algebra. And the transition function is given by those two equations here, and they are everywhere defined except when U and V are both equal to 0. So let's look at the picture that we have constructed with those three charts. We have theta and phi coordinates originating from the spherical coordinates that we use in R3. Then we have the UV coordinate system by projecting using the north pole, and the ST coordinate system by projecting using the southern pole. And all those maps here are differentiable, and the coordinate transformations between any pair of those coordinate systems, pair of those charts, is is smooth. Now let's move to another example. As we have already mentioned, Lie groups are also examples of differentiable manifolds. And the simplest one of those consists of the rotations of vectors on the plane. So if we have a vector v on the plane, and then we rotate it by an angle theta, we obtain a different vector, but whose magnitude has not changed. And you can show that if Vx and Vy are the Cartesian components of this vector, then the Cartesian components of the new vector are related to the previous ones by this relation obtained by multiplying this matrix, this column vector. So this rotation here is represented by the action of this linear transformation here, and this transformation is parametrized by the angle theta. So theta here defines a coordinate in the space of those transformations, and it is a nice and differentiable chart, but which of course does not cover the whole space of rotations. Similarly, if we consider such rigid rotations in space, we can define coordinates theta x, theta y, and theta z by considering first rotations with respect to each x, y, and z axis first. So if we take a vector v that now has three components, vx, vy, and vz, and we rotate it with respect to the x-axis first by an angle theta x, we obtain a different vector. Then, to this new vector, we apply a rotation with respect to the y-axis by an angle theta y. And to the resulting vector of this operation, we apply a rotation with respect to the z-axis by an angle theta z. So, the rotation defined by those three angles, theta x, theta y, and theta z, can be represented by acting with the product of those three matrices on the coordinates, on the Cartesian components of the vector. Another example is the example of the cylinder. As we have already mentioned, the cylinder is nothing but the topological space obtained by the product of the one-dimensional circle and the one-dimensional line of real numbers. And we have already said why this is so, because if we take such a circle here and we move it along this direction, which is equivalent to the real line, then we swipe in a continuous way the full cylinder. Another way to see the cylinder, this time not embedded in three-dimensional space, but on the plane, is to consider a strip on the plane that goes infinitely upwards and downwards, but we take those two lines and we identify their points. That is equivalent to, let's say, taking a pair of scissors and cutting this strip and then gluing those two sides the one to the other. And if you do this, then you obtain a cylinder in R3. But we can use this picture here, this representation, to understand what happens on the cylinder in a much simpler way. So, for example, let's consider this curve on the cylinder and understand what it is. So, this curve starts at the point A, moves on in this direction, and then, quote, quote, ends at this point here. But this point here is identified with this, with the gluing. So actually, this line segment here is not a line segment, but it is a circle. because if we move around here, we leave the strip in this direction, but we re-enter from the other side, and a motion around the circle here can be represented by a motion along the line here. So if we use this representation of the cylinder, it is easy to see that we can use a coordinate system U and V, which maps this strip here, except those two lines which are identified, onto the UV plane. So we take this coordinate here ranging from 0 to 2 pi, 0 and 2 pi excluded so that we don't include this line here, and the coordinate V ranging from minus infinity to plus infinity. And we map UV to a point P on the circle via this relation here. So this map is the obvious map that results from cylindrical coordinates in R3. And you see that with this choice, U corresponds to the angle that the position vector of P forms with the x-axis, and V corresponds to the Z coordinate of the point. A more interesting example arises when we also identify a line here with a line there. So we have this rectangle on the plane, and first what we do, as in the case of the cylinder, we identify this line with that line. So after doing this identification, we obtain a cylinder, like before. But then those green lines here become circles. And what we do is we identify them, we identify the bottom one with the top one. And after doing this identification is like taking this cylinder and gluing its bottom and top circles. And that will give us a surface that looks like a donut, shown here. So with this representation of the torus, we see how we can define coordinates U and V. So we can take U ranging from 0 to 2 pi without 0 and 2 pi included in the range, and similarly for V. And map a point UV onto a point on torus using these relations here, where now the point P on the torus is defined by x, y, and z. So with this map, the coordinates U and V have a simple geometrical interpretation. U is the angle that is formed by this direction, and V is the angle formed with those two directions, or what they actually are. So let's understand what happens when, let's say, U is constant. So when U is constant, only V changing, and we move around the circle on the donut. So this is this circle that has a radius equal to R1. This circle here has a center at distance R2 from the origin, so that R1 plus R2 cosine V is the distance of the projection of the point P onto the xy plane from the origin. So if we project this point onto the x and y axis, we obtain the x and y coordinates of the point P, given now by these relations here. Now R2 times sine V is the height of the point P from the xy plane, which is nothing but its z coordinate. So we have a chart on the torus that includes the whole torus with this set cut off. So we have to exclude the circle that corresponds to those red lines here, and the circle that corresponds to those lines there. So this takes a point on the torus xyz, the coordinates uv, where this relation between uv and xyz have to be satisfied. So let's study a little bit this representation of the torus on a rectangle more closely to understand it, because it is much simpler to look at the geometry of the torus on those rectangles than it is to look at them on its embedding. So let's consider a curve that starts from point A, moves on a constant u line up to here and arrives at this point there. But this line here and this line here correspond to the same points due to the identification that we have done between the green lines. So actually, this is a circle. And if you look at it at more details, using those relations here, you see that this is actually the circle that starts from here and ends there. Similarly, a constant v line that starts here, moves along constant v, ends there, will give us a circle that wraps around the torus in this direction. So v is now giving us the constant angle between the position of b with respect to the center circle. It does not change, but angle u is ranging from 0 to 2 pi. That moves us around here. Now let's look at more interesting curves. Let's consider a curve that starts at the point A1 here, and then it moves along those lines that are given by a linear relation between v and u, and it starts from A1 and ends up in A2. So moving a particle along this direction will start with v equal to 0 and end up with v equal to 2 pi. So the particle has done a full round around this direction of the torus. But in the end, it ends up at a different point, A2. So this point A2 is obtained by doing this full round around the circle and then going here at A2, which also has u equal to 0. So then you see we end up at the same point A2. We move on here along the spiral and end up at the point A3. But then A3 is identified with this point, and then we move to A4. From A4, we move to A5, and from A5, we come to this point, which is identified with that point, and we end up at the original point that we started from. Now, this is another more complicated example. We start from the point A1, let's say it is here. Then we move along this curve, and we reach the point A2. This point A2 has nothing special in its position on the torus, but on this rectangle here, I have to identify it with this point here. Now, let's see how the motion of the particle occurs on this curve. So if the particle is moving in this direction, then when it arrives here, it has to continue in that direction because the identification is done directions in both lines. So then the particle will now move from A2 and then reach a point A3 on this line. Now this is identified with this point A3, but now you see the point is moving downwards. It has to continue to be moving downwards. Then it continues on, reaches point A4, and then it makes a U-turn here, and then reaches a point A5 located here on the top line. Now it's moving upwards. A5 is identified with that point. Then the particle has now to continue moving upwards. And it reaches A6, 7, then back to A1. So we have this motion on this closed curve, and the motion is done on the same direction on the curve. The particle does not change direction of motion on the curve, although it seems so here in its cut-out version. Another example that is similar to the torus is by doing the identification in a slightly different way. So consider again a rectangle and identify those two sides as we have already done for the cylinder and the torus. So by identifying this and that, we obtain a cylinder. But now consider the bottom and top lines and do the identification in an opposite way. So we have somehow to twist the circle at the bottom so that it matches to the circle at the top. Then we obtained a manifold that is topologically inequivalent to the torus, and it's called the Klein Bottle. And it has the property of being non-orientable. And as we will soon see, it's not even embeddable in R3. Of course, it's embeddable in R4, but this will not help us very much visualizing manifold using an embedding. So in the Klein Bottle case, it is much simpler to consider this representation here on the plane than try to imagine its immersion in R3. So let's see what happens as we move around the Klein Bottle. First of all, if we have a point C on this side, this is identified with that point C on the other side. But now, if we are on the blue sides, the identifications have to be done the opposite way. So if we have a point A at the bottom line here, this has to be identified with that A on the top line. And the point B on the bottom line has to be identified with that point B on the top line. So this is what it means to glue those two lines the opposite way. So let's consider curves. Let's consider this curve here obtained by this line segment. It starts from here, it moves to the right, and arrives at this point here. But this point here is identified with that point here. So actually, if a particle moves around this line here again and again, it actually moves on a circle, on a closed curve. Now, if we want to define such a quote-quote circle on the Klein Bottle by moving in the other directions, if we start from that point here, we have to go and end up at a point that is identified on the opposite line, which will be that point here. So now we cannot move in this direction, in the vertical direction, because if we do so, we go around here and then reach that point, but this point here is not the same as this point. It is that point there. So actually we have to repeat going vertically up and make, wrap around twice to reach the same point here. But, okay, let's consider the simplest case where we move directly from here to there. So this is a loop that closes, and it is equivalent to a circle. Now, let's look at this more complicated motion of a particle on the Klein Bottle. So let's start here at the center and move in the direction of the arrows. So first, we reach the point C. C is identified with that point C. So the particle is moving downwards. It will continue to move downwards along the direction shown by the arrow. And then it will reach point A. Now, the point A is identified with that point and not with that point. So the particle will leave the rectangle from here and will re-enter from there. And also notice the change of direction of the motion on the rectangle. Here, the particle is moving towards the right. Now, because the identification is done the opposite way, here it will appear moving to the left. But it is actually not changing direction on that curve on the Klein bottle. So we go on, move around the curve, and then we reach the point B. The point B is identified with the point here. So the particle is leaving the rectangle here, and it is re-entering from there, and then it reaches again the center of the rectangle, closing the curve. So let's see how we can draw a surface of in R3 that has the topology of the Klein bottle. So let's start by doing the simplest of the things, which is to identify this side with that side. So we cut this rectangle and we glue those two sides and we obtain a cylinder. But now we cannot glue the top and the bottom like we did on the torus, because the direction of the gluing is opposite here and there. So we somehow have to twist the bottom circle so that its direction matches with the circle that we are planning to glue it with. So we do topologically equivalent operations by stretching this cylinder, imagining it that it is like an elastic band or something. But now it also has to be somehow like a phantom elastic band, because we have to pull it through this part of the cylinder. And then we take it out that way here. So after we do this operation of stretching the cylinder, we see that those two circles have directions that don't match, that cannot be glued directly. Actually, what we have to do is to twist this cup, stretch it this way so that the two circles find each other in the same direction, and then we can do the gluing. But in the process, you see that this surface has to cut itself. So this is not actually an embedding of the Klein bottle, but it is a map which is called in mathematics an immersion. And this is actually how this immersion looks like. Then we can define coordinates u and v on the Klein bottle, such that we can map this range of u and v onto the x, y, and z coordinates of the points on the surface. As we have already mentioned, it is a theorem that the Klein bottle, like any two-dimensional manifold, can be embedded in R4. And here, so how can this map be done and obtain a four-dimensional embedding of the Klein bottle, and in that case the surface does not intersect itself. It's not a self-intersecting surface.